All right, in this video, we are going to move into section 7.4, which is titled Integration by Partial Fractions. So some good news, we're kind of moving away from some of the trig integrals that we just finished up in the last material. We're going to move into something a little bit more algebra-based, so maybe this will be a little bit more of a cup of tea for some of y'all who didn't like all the trig stuff we just did. All right, so here's kind of the idea for this section. Let's kind of go back to algebra for a second and kind of let me show you what we're about to do. So back in an algebra class, your teacher will probably have given you something that looks like this, which is called a rational expression. And the job you had to do was figure out how to put them together by getting common denominators and all that good stuff. And going through the process, you could eventually show that these two fractions subtracted into this one big rational fraction. Now, what we're going to do today is actually go the opposite direction, because what we're going to be given today is an ugly rational function and be asked to integrate it. The problem is that integrating that particular function that I have boxed in purple is not very easy. So what we're going to do is we're going to break it down and try to turn it into simpler fractions and therefore make it a little bit easier to integrate. So in the end, what the goal is to take something like x plus 5 over x squared plus x minus 2, break it down into these two rational functions, and then you can look at both of these and see that both of them actually integrate into relatively easy functions. In this particular case, they both become natural logs. So it would be 2 times the natural log of x minus 1 minus the natural log of x plus 2 plus an arbitrary constant. Now, most of the problems in this section, the integration is not going to be the hard part. It's going to be, can we get our complicated function down into simpler fractions that integrate relatively easily? And what we're going to talk about the next little bit is different techniques of how that works. So let's begin with the very first technique that you can do. So it is always possible to express f of x as a sum of simpler fractions. That's usually going to be our goal. Now, there is a catch to this. If the degree of the numerator is greater than the degree of the denominator, you must first do long division. All right? So this is also going to be true when the highest degree is the same in both the numerator and the denominator. So first thing we will always look for is that if the power on top is either equal or bigger than the highest power on the bottom, the only way to simplify this up front is to do long division. So let's review what long division says back in algebra. You would take your numerator, which is x cubed, and I'm going to put some placeholders in as well. So how about plus 0x squared and then plus x? And we want to divide this by the denominator, which is x minus 1. And what your goal is to figure out what can you multiply x minus 1 by so that it keeps canceling some of these terms. So the first thing I'm going to divide into it is x squared. Because if I were to multiply x minus 1 by x squared, that would give me x cubed minus x squared. Remember back in like 3rd grade division, you would subtract these two terms, which very nicely would cancel the x cubes, and then 0x squared minus a negative x squared would be a positive x squared, and then you would bring down the plus x. And you'll continue this until you can't divide it anymore. So the next thing I would go into is to get rid of the x squared, I have to do a plus x, because x times x is x squared, and x times negative 1 is negative x. I'm going to subtract both of those again. Once again, the x squareds cancel like I want, and x minus a negative x is 2x. Now that the powers match, this will be the last time you have to do it. So to get rid of the 2x, I've got to divide by a plus 2, or multiply by a plus 2, I guess. So that would give me a 2x minus 2, which I'm going to subtract from that. And this will cancel the 2x's. And remember, there actually is an understood 0 here. So 0 minus a negative 2 is positive 2. So the last thing to remember back in long division is that when you go to rewrite this problem, so now I'm going to write my new fraction. What divided into it? Well, that was the x squared plus x plus 2 that we found here in red. And then whatever your remainder is, you must divide your remainder by the original denominator, because that part still has to be there. And now you can see we've taken an ugly rational function that was not very easy to integrate and turned it into 4 pieces that are all very simple to integrate. So this would become x cubed over 3 plus x squared over 2 plus 2x plus 2 times the natural log of x minus 1 plus an arbitrary constant c. And that is going to be your first technique of how you simplify rational functions. If the power on top is bigger or equal to the power on the bottom, you need to do long division to simplify this. Now, the bigger case we're going to run into for most of today is exactly the opposite. What happens if the power on top is smaller than the power on the bottom? Then long division cannot be used, and you need another technique in order to do that. This is where the idea of partial fractions comes into play. So before we get into all of the different ways that partial fractions work, a little bit of background about what we're going to do. So number one is probably the most important thing. Partial fractions can only be done if the denominator is fully factored. So if I don't give you a factored denominator, you must factor it first before continuing on into one of the 4 cases we're about to talk about. So what it can be shown is that, at least the problems that we're going to do, it can be shown that any polynomial in the denominator can be factored as either a product of linear factors, like ax plus b, and irreducible quadratic factors, like ax squared plus bx plus c. Remember, irreducible just means that it doesn't factor. So you'll get a quadratic that doesn't factor any further. Officially, that means the determinant of it is going to be less than 0, but don't worry about that part. That's just a little extra that I put up here. So let's break down the 4 cases that we're going to run into today. And they kind of go from easiest to more difficult. So case number 1, if your denominator is a product of distinct linear factors, so it's things like x plus 1 and x minus 2 or something like that. They're all linear and they're all distinct. Then you can break up your fraction into the number of fractions that will generate is the number of distinct linear factors that you have. So if you've got 2 distinct linear factors, you'll break this up into 2 separate fractions. Now the challenge for us is going to be on top of these fractions are going to be unknown constants and functions that we've got to solve for. So in a case 1 partial fraction, all of your numerators will be constants like a, b, c, etc. that we will have to solve for. And I will show you how to do that when we get to the problems. Case 2 is when your denominator is the product of linear factors still, but what if some of them repeat themselves? So what if in the denominator you had something like x minus 3 all squared? So x minus 3 is a linear factor, but if it's repeated, this causes you to do a case 2 partial fraction. Now, the only difference you will have to worry about here is that if it's repeated, you have to include every term starting at 1 up to the power of the repeated factor. So if it was a squared term, you would need 2 fractions to break that down. If, for example, it was an 8th power, which we will not do, you would have to do 8 fractions to break that down. That's kind of the idea. Now, do note that even though it's being repeated, the inside of each of these factors by itself is still linear, which means on the numerator, we will just put unknown constants that we will have to solve for eventually, all right? So anytime you deal with linear factors, the top of the fraction is always just constants. Where that changes is when you get into things like case 3 and case 4. So case 3 is, what if you have an irreducible quadratic factor in the bottom that doesn't repeat? So what if in the bottom you had something like x squared plus 1? That's a very simple irreducible quadratic. So anytime an irreducible quadratic pops up in your partial fractions, in the numerator of that, you have to actually put an unknown linear function. So above every irreducible quadratic factor, you will put an x term and a constant added together, but both of those variables are going to be unknown. So we'll do something like ax plus b. And then finally, case 4, which we don't do a lot of, but I did find one today that works out pretty nicely. We're going to do case 4, which is a repeated irreducible quadratic factor. So just like case 2, when you repeat irreducible factors, you have to treat them as separate. So you have to include a fraction that does every power starting at 1. So if it was a squared, you would need 2 factors. A cube, you'd need 3 factors, and so on. But keep in mind, inside each of these factors, no matter what power we have to go to, is an irreducible quadratic. So in the numerator of each one is still going to be that same idea of a linear function like case 3. So if you needed 2 of them, you would do like ax plus b, and then you would do cx plus d, and so on. You would use the next letters in line and have to solve for all of those, which does get a little more complicated because the more letters, obviously, the more work you have to do. Now, each case separately, just by itself, is not very difficult. What we're also going to see as we go further along in this section is what happens if the cases are combined. What if it's a part case 1 and part case 3, or 2 and 4, or etc.? We're going to look at all of that today as we work these problems out. So what we're going to do now is we're just going to work through some problems. I try to put all 4 cases at some point in this section, so we will talk through what case falls on which problem, and then I'll show you how to work each type of problem. So let's begin with this one. So example number 1. Integrate the function x minus 4 over x squared minus 5x plus 6. So with this type of problem, I see the rational function here, but the very first thing I told you to always do is you need to factor the denominator. So if you were to factor the denominator here, that would be x minus 2 and x minus 3. Because now you can see that the bottom of this fraction are 2 linear factors that are different. So that tells me that I'm going to do a case 1 partial fraction. So what you do here is we got to break this up. We don't want to leave it in this form. So over here on the right, we're going to always do some scratch work, sometimes more than others. I'm going to take my factored quadratic function, and I'm going to break this down into the number of fractions that are needed. Now, in case 1, every single distinct linear factor has to get its own fraction. So x minus 2 gets a fraction, and x minus 3 gets a fraction. But since they're linear, you just have to put an unknown constant on top, but I'm just going to go in alphabetical order every time. We'll call that a and b. So now your job is to figure out what a and b are, and there are a number of ways to do this. My first instinct every time is I'm going to always multiply all 3 fractions, or however many fractions there are, by the original factored denominator, because that's a guaranteed way to get rid of all of your fractions. So when I do that, that will become x minus 4 on the first one, because everything cancels. On the a fraction, the x minus 3 doesn't cancel. And on the b fraction, the x minus 2 doesn't cancel. Now, one of the good things about case 1 partial fractions is that there's actually a shorter way to solve for the constants than what we're going to see later on. So I do want to teach you this shorter way because it will save you a little bit of time in case 1. We're going to do what I like to call the plug and chug method, because since this is just a equation, you can plug any value of x you want to and solve for the whatever letter is left. So what I'm going to do is I'm going to very cleverly pick an x value that makes the a term go to 0. So if I let x equal 3 in the entire equation, 3 minus 4 is negative 1. The a term goes to 0, so it's not there. And then 3 minus 2 is 1 times b is b. And as you can see very nicely, we just found b to equal negative 1. Doing the exact same thing, but now I'm going to try to get rid of the b fraction. Why don't I let x equal 2? So from left to right, 2 minus 4 is negative 2. 2 minus 3 is negative 1, so you get a negative a. And if you divide both sides by a negative 1, we have found that a equals 2. Now all you have to do is now we're going to come back to my original problem back over here in purple. And we are going to integrate from 0 to 1. I'm going to take both constants that we just found and substitute them into my partial fraction breakdown, and then we'll work the problem. So a was 2, so we're going to do 2 over x minus 2. B is negative 1, so that's plus a negative 1 over x minus 3 dx. Integrate both of those functions, so you will get 2 times the natural log of x minus 2 minus the natural log of x minus 3, and we're going to evaluate all of this from 0 to 1. So if I go through and plug 1 into both of these functions, you should get 2 times the natural log of 1, because remember you're applying the absolute values, minus the natural log of 2, minus, then go through and plug 0 in, and you get 2 natural log of 2 minus the natural log of 3. Now, the one good thing about this one is that the natural log of 1 is just 0, so I can get rid of that term. And if I distribute the negative to the second parentheses, you get negative natural log of 2 minus 2 natural log of 2 plus the natural log of 3, and then put your natural log 2 terms together, and you get negative 3 natural log of 2 plus the natural log of 3. And that is your first example of a case 1 partial fraction. Now, that one not only let us test our skills on breaking the fraction down, but since it was a definite integral, we had to go a few extra steps and actually evaluate each part. So, but not every single problem will be definite. We'll see a couple throughout this section. All right, so let's look at example number 2. I want you to integrate 5x plus 1 over 2x squared minus x minus 1. So once again, the issue with this fraction is that the bottom is not factored. So let's figure out what we would factor the bottom into. So it looks like we could factor this into, let's see, 2x and x, 1 and 1. And if you want a minus in the middle, it's got to be plus minus. So it will factor into 2x plus 1 and x minus 1. Once again, I need to now break this fraction down into simpler fractions that can be integrated. So I'm going to take 5x plus 1 over 2x plus 1 and x minus 1. Now, both of those are linear factors, and they are both different, so they each have to get their own fraction. So my first fraction will have a 2x plus 1 on the bottom. My second fraction will have an x minus 1. And since they're linear, we just put an unknown constant on the top of each one. And then once again, what I like to go ahead and do is I'm going to multiply everything by the original factored denominator and distribute that through to get rid of all of these fractions. So multiplying it by the first fraction will give me a 5x plus 1. On the a fraction, you'll still have an x minus 1 left over. And on the b fraction, you will have a 2x plus 1 left over. And once again, since this is a case 1 partial fraction, I can use what I'm calling the plug and chug method to solve for my coefficients easier. So to get rid of my a constant, I'm actually going to let x equal 1, so that way I know it goes away. So let's see, 5 times 1 plus 1 is 6. And on the right, that's 2 plus 1 is 3, so you get 6 equals 3b. If you divide both sides by 3, we can see that b is going to equal 2. Now, using the other value, to what x value you have to plug in here, looks like you've got to let that be negative 1/2 in order for that to go to 0. So if you plug negative 1/2 into everything, that would be negative 5/2 plus 1, which is negative 3/2. And then negative 1/2 minus 1 is negative 3/2 a. Well, in order to make this statement true, we could just say that a is going to equal 1. That's the only value that would make this statement true. I am now going to sub both of my constants into my breakdown of the partial fractions, and I'm going to rewrite my integral over here on the left. So you should be able to rewrite this as 1 over 2x plus 1 plus 2 over x minus 1 dx. And since this is an indefinite integral, we just have to integrate each term and get the final answer. Now be careful on that first fraction because it will be a natural log, but you're going to have to put an extra constant on top to make it work. So remember, if you multiply the top by 2 to make it a natural log, you've got to put a 1/2 out front. So this becomes 1/2 times the natural log of 2x plus 1. And on the top one, you can just bring the 2 out front and make it plus 2 times the natural log of x minus 1 plus an arbitrary constant c. And that is your second example of a case 1 partial fraction. This one was just indefinite, so it went a little bit quicker once we got all the letters solved for. So now let's move into some that aren't case 1 partial fractions. So these are going to take a little bit more time to solve for the coefficients. So what about this number 3? What is the indefinite integral of x squared plus 1 over x minus 4 times x minus 3 cubed? Now, the good news up front, at least, is that this is already in a factored form on the bottom, but this doesn't integrate as it sits. So we're going to have to still break it up. So if I were to rewrite my fraction over here, x squared plus 1 over x minus 4 times x minus 3 squared. Excuse me. Since there is an x minus 4, which is a linear factor, that's a case 1. I'm going to need one fraction to break x minus 4 up. And since x minus 3 is linear, but it's repeated, I'm going to need 2 fractions to break up the x minus 3. One of them would just be the first power, which is x minus 3, but you also need another fraction for the second term because you have to include every factor from the first power up to your final factor. Now, overall, they are all just linear factors separately. So on the top, we're just going to get a bunch of constants. So this time we've got to solve for an A, a B, and a C. Other than that, the first initial step to solve for these is going to be the same for me. I'm going to multiply everything by the original factored denominator. Make sure you distribute it to all 4 fractions. When I do that, you're going to be left over with an x squared plus 1 equals A times x minus 3 squared plus B times x minus 4 and 1x minus 3 term. And then on C, you would just have the x minus 4 term. Now, while you could start off by doing the plug and chug method here, you're not going to be able to solve for all the constants doing it that way because of the repeated terms. So therefore, it's actually just going to be easier to expand all of this and then solve it a different way because we'll need this technique in the case 3 and 4s. Oh, and by the way, this is a case 2 partial fraction because it's a repeated linear term. So if I were to expand everything on the right, that would be A times, that becomes x squared minus 6x plus 9 plus B, FOIL these two terms together, and you get x squared minus 7x plus 12, and then plus C times x minus 4. Distribute your constants through, or your unknown constants, I guess I should say. So that would be ax squared minus 6ax plus 9a plus bx squared minus 7bx plus 12b plus cx minus 4c. So what I'm going to do now is we are going to set up a bunch of simultaneous equations that we can solve based on the coefficients of the powers on the left and the right. So what I mean by that is if you look at the left-hand side, there is an x squared term, but its constant is 1. On the right, you want to pick out all of the constants that have an x squared. So that would be this a, and you would have this plus b. So therefore, I know in the end a plus b will have to equal 1 to make this a true statement. There are no x terms on the left, so I have to call that 0. And then if you pick off all the x coefficients on the left, there's a negative 6a, then I see there's a minus 7b, and then a plus c, which all of those will have to combine to be 0. And finally, on the left, the solo constant is 1. And then if you pick off all the coefficients that don't have x's involved on the right, that would be 9a plus 12b minus a 4c. And now we've got to figure a way to solve all of these variables simultaneously, which is a little bit more difficult than the last couple, but I'll show you how to do it. I'm going to start with the easy equation, and I usually just pick a letter to solve for. It doesn't really matter. Let's get a by itself. So if I move the b over, I could say that 1 minus b equals a. So that means in my second equation, why don't I let a be 1 minus b? So that would be 0 equals negative 6 times 1 minus b minus 7b plus c. So then I'm going to work this out. This would be 0 equals negative 6 plus 6b minus 7b plus c. All right, and then I could say that 0 equals negative 6 minus b plus c. All right, I have an equation for a in terms of b. So what I need to do on the second equation is that I now need another equation for b with a different letter. So I'm going to have to get c by itself here. When I do that, I'm going to move the negative 6 and the negative b over to say that 6 plus b will have to equal c. Because now what you have to do to finally wrap this up is that in your third equation, if I let this a be in terms of b, and I let this c be in terms of b, there's already another b, and I'll finally be able to start solving for the constants directly. So if I start plugging my information on the third equation, we will have 1 equals 9 times 1 minus b plus 12b minus 4 times 6 plus b. And I just substituted in my two equations. Work this out, and you'll get 9 minus 9b plus 12b minus 24 minus 4b. All right, so let's see. There's a 9 minus a 24, so that's going to be a negative 15 in this case. Then if you put all of your b's together, you're going to get, let's see, that's 3b, that's minus b. Move the 15 over, so you get 16 equals negative b, and then getting the b by itself should show you that b is going to equal negative 16. But once you get one letter solved for, we can now plug this back into your other two equations to solve for a and c. So on the first one, you would have 1 minus a negative 16 equals a. So therefore, a would actually equal 17. And then plugging b into the second equation, you would have 6 minus 16 equals c. So therefore, you'd have negative 10 equals c. And that is by far the harder part of this problem. But finally, after all that work, which that's the hardest part here, you have solved for a, b, and c. And we now need to plug all three of those constants back into my partial fraction breakdown, and then we have to actually go through the process of integrating. So over here on the left, when I start to rewrite the problem, this will be the indefinite integral of 17 over x minus 4 plus a negative 16 over x minus 3 plus a negative 10 over x minus 3 squared dx. Now, those first two fractions actually integrate very easily. They are both going to, once again, just be natural log functions. So you would have 17 times the natural log of x minus 4 minus 16 times the natural log of x minus 3. But this second one doesn't actually factor. Or actually, doesn't actually integrate into a natural log. Sorry, I said the wrong word. But what I could do is I could factor that negative 10 out, and then I can just integrate 1 over x minus 3 all squared dx. Now, the only way to integrate this function is we're going to have to do a u substitution here. So what I'm going to do is I'll go back to green here. I'm going to let u be x minus 3. So therefore, du would actually just equal dx. And I'm just working on this third piece. These first two terms, I'm just going to leave them alone. So this would be minus 10 times the integral of 1 over u squared du, which can be rewritten as negative 10 times the integral of u to the negative 2 du. We can integrate that. So this is now negative 10 times. Add 1 to the power and divide by the power, which is u to the negative 1 divided by negative 1. If I bring that negative 1 out, it becomes a plus 10. And if I rewrite u to the negative 1, that would just be 1 over u. All right, so we can now kind of put all this together. I can bring these two original integral parts down, because remember, those didn't change throughout the entire u sub part. So you would have 17 times the natural log of x minus 4 minus 16 times the natural log of x minus 3. Putting these together would be plus 10 over your u term, which we know to be x minus 3. And then in the end, now that we're done, this is an indefinite integral, so we have to add a plus c on the end, and that is your final answer. So you can see that once you move past case 1, it gets a little bit more difficult, especially in the algebra part of this. So just kind of be ready to solve for these unknown constants using this new technique. All right, so let's move on to another one. Number 4. What is the indefinite integral of 10 over x minus 1 times x squared plus 9? Now, just like number 3, this one is already in a factored form because x squared plus 9 doesn't factor any further, so there's not much I can do with that. So what I'm going to do is going to go ahead and come over here to the right, and we are going to figure out how to break down this fraction here. Now, going piece by piece, x minus 1 is just a linear factor, so it's going to get a fraction by itself. And for the first time, we have an irreducible quadratic, which is x squared plus 9, that we will have to give its own fraction. Now, since that is an irreducible quadratic, this does become a case 3 partial fraction now. But keep in mind, since the first fraction is linear, it just gets a constant on top. But since the second fraction is an irreducible quadratic, you've got to put a linear factor on top. So I would have to express that as bx plus c. That's the big difference here. Now you've got to go through the process of solving for all 3 variables. So I'm going to multiply everything by x minus 1 and x squared plus 9. When I do that, you should have left over a 10 equals a times x squared plus 9, plus the bx plus c will be multiplied by an x minus 1. Multiply out what you can on the right. So 10 would equal ax squared plus 9a plus bx squared. So we're foiling here. Bx squared minus bx plus cx minus c. And now I'm going to set this up just like I did the last problem and do constants. So on the left, there is not an x squared term, so I will call that 0. But on the right, I see that I have an a plus a b with x squared. So I know that a plus b must equal 0. There are no x terms on the left, so I'm going to call that 0 again. But on the right, I see that I have a negative b plus c that must combine to be 0. Finally, there is a constant on the left of 10, and on the right, we have the constants of 9a and a minus c. So I need to solve all of these equations directly. All right, so let's see. Kind of approaching this the exact same way. I need to get one of these equations all into the same letter. So kind of like the last one. On the first one, I'm just going to get A and B on the different sides. So I can say that A equals negative B. On the second equation, kind of the same idea. I'm going to move the B over, and I can see that C and B must be the same thing. What that now allows me to do is on this last equation, I can turn this A into a negative B and turn this C into a B, and I can at least get one of my letters solved for. So this would be 10 equals, since A equals negative B, this actually becomes negative 9B. And since C and B are the same thing, this just becomes minus B. That means I can solve for B now. 10 would equal negative 10B, and therefore B would equal negative 1. Use that B value to help you get A and C solved for. So since A is the opposite of B and B is negative 1, that means A has to equal positive 1. And since B and C are the same thing, I can see that C has to also be negative 1. All right, so we did all the hard work now. We're going to substitute these variables back into my partial fraction breakdown, which will be the indefinite integral of 1 over x minus 1. All right, and then plus B and C are both negative 1, so that's negative x minus 1 over an x squared plus 9. And we're going to integrate this with respect to x. All right, so first thing, when I look at this, that first fraction, I know how to integrate that. So that's going to end up just equaling a natural log of x minus 1. And there's always at least one, there's usually at least one natural log in most of these problems. The second fraction, I see that the top two terms share a negative in common. So why don't I factor a negative out in front of the integral and make this a positive x plus 1 over x squared plus 9. That way it looks a little bit nicer. Now, unfortunately, this does not integrate directly. There's nothing we can do here. But since the bottom doesn't factor any further, doing more partial fractions is not the go-to here. So instead, we're going to go back to a different technique that we did earlier in this class, and we're going to break it up a different way. So remember, that natural log term will sit there until we're done. What I'm going to do is, since the bottom is as best as it's going to get, because there's not another term, why don't we take each term in the numerator and divide it by what's on the bottom? So I can write this as x over x squared plus 9 plus a 1 over x squared plus 9. These are now two fractions that we should know how to integrate, but I'm going to probably remind you about one of them. So once again, just focusing on the integral here. The x over x squared plus 9 actually does become a natural log, but you'll need to put a 2 on top for it to work, which means you have to put a 1/2 out front. So there's actually a 1/2 times the natural log of x squared plus 9. And that's how you integrate the first fraction. This second fraction is one of those rules that we went over at the beginning of 7.1 that I said that you would have to know throughout the rest of this class because they randomly show up. So 1 over x squared plus 9 looks strangely familiar to the rule 1 over u squared plus a squared du, where that actually integrates into 1 over a times the inverse tangent of u over a. Well, in our case, u could just be x, and a is going to actually be 3 because that's the square root of 9. So it can be shown that this integrates into 1/3 times the inverse tangent of x over 3. And that's how we have to go through that. That's why I said knowing those rules is vital, because they do show up a good bit in these later sections. All right, so let's put everything together for our final answer. This should be the natural log of x minus 1, and then don't forget to distribute the negative, minus 1/2 times the natural log of x squared plus 9 minus 1/3 times the inverse tangent of x over 3, And now that I'm done, this is an indefinite integral, so I will put a plus c on the end. And there's your first example of a case 3 partial fraction. All right, so let's go on to another one. What is the indefinite integral of 3x squared minus 8x plus 8, all divided by x cubed plus 4x? Now, we haven't done this in a while. The last few problems have been factored for us, but this is our next one that is not factored. You need to factor the denominator, because first thing I know is we don't have a rule for cubes. So that means I'm probably pretty sure this factors in some way. Now, it doesn't do much. You're going to have 3x squared minus x plus 8. And on the bottom, all you can really do is factor an x out to make it x times x squared plus 4. But now you can see that this is two parts that we can actually deal with. So come over here to the right. If I take my factored form of the original function, we're going to break this down. Now, x is just a linear factor because it's the same thing as like x plus 0. So x is going to get its own fraction. And then x squared plus 4 is an irreducible quadratic. It doesn't factor any further. So this is once again another example of a case 3 partial fraction, where the x is going to have to end up having an a on top. It's just a linear term. But the irreducible quadratic is going to have a linear term on top, which is bx plus c. And I just realized that I don't know why I kept this in purple, but I'm not going to change it now. I've been doing red, so I apologize for that. So we are going to multiply everything by the original factor denominator. Done that every time so far. I'll change the red at this point now. So you're going to have 3x squared minus x plus 8 equals a times x squared plus 4 plus bx plus c times x. Expand those terms on the right, and you should get 3x squared minus x plus 8 equals ax squared plus 4a plus bx squared plus cx. So let's set up our simultaneous equations. On the left, you have an x squared term of 3, and on the right, you've got two x squared terms of a plus b. So those have to add up to equal 3. On the left, your x coefficient is -1, and here's the better part of this problem. The only x constant on the right is c, so right away, I know that c has to be -1 for this statement to be true. On the left, a constant is 8, and on the right, the only constant we have is 4a. So if I divide both sides by 4, I can automatically say that a has to equal 2. Now that I know a is 2, I can use that to help me solve for b. So 3 will equal 2 plus b, and therefore b is going to equal 1. Substitute all three of those constants back into your broken down partial fraction, and let's figure out how to integrate this. So this will be the indefinite integral of 2 over x plus, we're going to end up with an x minus 1 over x squared plus 4 dx. Now, very similar to the case 3 partial fraction we just did, that first term, you can integrate that directly. That's going to be 2 times the natural log of x. And then just like the last one, this one is going to need to be broken down like we did number 4 into 2 separate fractions. So it would be plus the integral of x over x squared plus 4 minus 1 over x squared plus 4 dx. Both of those terms can now be integrated directly just like we did on number 4. So this will end up being 2 times the natural log of the absolute value of x. On the first fraction, I need a 2 on top to make this a natural log, so I'll have to put a 1/2 out front to make it 1/2 times the natural log of x squared plus 4 minus, and then this is going to integrate using that same inverse tangent rule, except your a value will be 2 versus 3 this time. So it'll become minus 1/2 times the inverse tangent of x over 2. And since it is an indefinite integral, please don't forget your plus c on the end when you put your final answer. And there's another example of a case 3 partial fraction. Just this one, you had to factor up front to notice that. All right, and last but not least, let's do one more. We haven't done case 4 yet, so let's wrap up this first part of this section with a case 4 partial fraction. So what is the indefinite integral of x squared plus x plus 1 over x squared plus 1 all squared? Now, this is already in a factored form. You're not going to be able to factor this any more than it already is. But when I go to rewrite this and start talking about the breakdown, so we put the problem over here on the right, I notice that x squared plus 1 is an irreducible quadratic, but it's being repeated twice because of the square. All right? So what I'm going to do is I'm going to need one fraction for the first term of x squared plus 1, but I also need a second fraction for the second term of x squared plus 1 since it's repeated. Both of those by themselves are irreducible quadratics. So on top, both of them need linear functions. So I'll have to put an ax plus b on top of the first fraction and a cx plus d on the top of the second fraction. All right, so other than that, this problem works very similar. I'm going to multiply everything by the original denominator, which is already factored. This will end up giving me x squared plus x plus 1 equals the ax plus b has to be multiplied by another x squared plus 1 term. And in the last term, you're just left with the cx plus d. Expand those first couple terms. So x squared plus x plus 1 is going to be ax cubed, all right, plus ax plus bx squared plus b plus cx plus d. Now, even though there is not a cubed term on the left, you're going to have to start with that because there is a cubed term on the right when we expanded this. So note cubed on the left means it's a 0. And since the only cubed term on the right is a, I know right away that a has to be 0. X squared on the left has a constant of 1. X squared on the right, there's only a b. So this is coming out really nice. I know that b has to equal 1. For your x terms, there's a 1 on the left. And on the right, there is an a plus c. But remember, we already know that a must be 0. So by default, I know that c has to equal 1. And then your constant on the left is a 1. And your constants on the right are going to be a b plus d. But once again, we already know from the second term that b has to be 1. So I know that 1 has to equal 1 plus d. And then moving that 1 over, we now know that d has to also be 0 like a was. Plugging these 4 constants into our partial fraction breakdown will allow us to do the following. We are going to integrate, so that's going to end up being 1 over x squared plus 1 for the first fraction, and your second fraction will become x over x squared plus 1 all squared. Now, that first fraction is a direct integral. That is something that's not even a fancy rule. That's just a regular inverse tangent function. So this will be the inverse tangent of x, and then you're going to have to integrate x over x squared plus 1 all squared. Now, the only way that I can see, how to integrate this is going to end up being a u substitution. So I'm going to let u equal the inside function, which is x squared plus 1. So therefore, du has to be 2x dx. So du over 2x is your value of dx. Now, the inverse tangent's not going to change, so I'm not going to worry about that piece. I'm just going to work on this second integral. This will be plus the integral of x over u squared times du over 2x. Very nicely, the x's cancel, and I can rewrite this as 1/2 times the integral of u to the negative 2 du. Integrate that function, and that would become u to the negative 1 over negative 1, which will end up becoming, oops, not plus, because I'm going to bring that minus out front. Let me erase that, sorry. If I bring that negative 1 out front, it actually becomes a minus 1/2 times, and then rewriting the u, you get 1 over u. Take this inverse tangent from the beginning, and we're going to bring it down so I can write, and I'm actually going to write my final answer over here on the right where there's more room. You should end up with an inverse tangent of x minus a 1/2 times 1 over u, which would be 1 over x squared plus 1, and then don't forget your plus c. Now, if you want to put those two terms right there together, you are more than welcome, but I would actually take it if you just leave it just like this. And that is an example of a case 4 partial fraction, because it had a repeated irreducible quadratic factor. Now, the one thing to be careful about in this section is that when we're doing partial fraction problems, I always have students assume that everything is a case 1 through 4 because they're not paying attention. But sometimes I will sneak a problem in like this that we did a little bit earlier in the video. So what is the integral of x cubed plus 4 over x squared plus 4? So actually, in the big scheme of things, this is not even a partial fraction problem. Because if you look, remember the first rule, one of the first rules I told you, if the power on top is bigger than or equal to the power on the bottom, you have to actually do long division in order to work this, not partial fractions. So don't even do partial fractions. Let's set this up as a long division problem. So it would be x cubed plus 0x squared plus 0x plus 4 needs to be divided by x squared plus 4. All right, so in order to get rid of this, I would have to multiply by an x, which would give me x cubed plus 4x that I need to subtract from this. Well, very nicely, the x cubes cancel. I would bring down the 0x squared. 0x minus 4x is negative 4x. And then bring down the plus 4. All right. So in this case, you actually can't go any further because the x squared can't be divided into the negative 4x plus 4. So that's the best you're going to get. When I rewrite this problem, that means I'm going to have an x, and then I have to add to this my remainder, which is negative 4x plus 4 over x squared plus 4 dx. We actually saw this idea a little bit earlier today when you have this irreducible quadratic left over and it doesn't integrate perfectly. You need to break it up one more time using a different strategy. So we can actually do this as the integral of x. Oops, sorry, apologize. We can go ahead and integrate x as x squared over 2. All right, and then I'm going to do plus the integral. And I can write this as negative 4x over x squared plus 4 plus a 4 over x squared plus 4 dx. We saw this when we did the case 3 partial fractions. So each of these integrate very nicely, maybe with a little bit of manipulation though. So this would actually be x squared over 2. All right, so that minus 4, if you want to, you can bring it to the front. And if you integrate the x over x squared plus 4, I think we actually saw that one earlier today. It comes out to be 1/2 the natural log of x squared plus 4. All right, so that would be the first part. And then the second fraction, if you factor the 4 out front and you integrate 1 over x squared plus 4, that's that inverse tangent rule we covered earlier. So you would actually get 1/2 the inverse tangent of x over 2, and then in the end, you're going to have a plus c. Now, we can combine some constants here, so you're going to end up with a final answer of x squared over 2 minus 2 times the natural log of x squared plus 4 plus 2 times the inverse tangent of x over 2 plus your constant c. And this, oops, sorry, it's a horrible box. This is your final answer. And so just be careful. Not everything is a case 1 through 4. If your power on top is bigger or equal to the power on the bottom, you will have to instead do long division to set it up and break down the fractions. Just be aware of that when you're doing your assignments. Now, in the big scheme of things, partial fractions have a big variety of what you can do. Every problem that I picked out today so far have been problems that were relatively simple in the big scheme of things, but in the real world, there are problems that are very complicated that partial fractions can be done with, but usually you will use a computer algebra system to help you out. So what I want to do on the next 2 problems to wrap up this video is I would like to, I would like to show you how to break these down and how they would work, but we're not going to actually solve them all the way out. So for the next 2 examples, I want to do the following. Write out the form of the partial fraction decomposition, which is just a breakdown, but do not figure out what the coefficients are. So we're not going to solve for the A, B's, and C's. I just want to see if we know how to break these down. Now, on the first fraction, I've given you x to the 4th minus 2x cubed plus x squared plus 2x minus 1 all over x squared minus 2x plus 1. So on its surface, if you look at this very carefully, this is actually not a partial fraction problem yet because the power on top is bigger than the power on the bottom. So just like the problem we just did, you're going to have to actually do long division to start this out. So we're going to take the numerator and we are going to divide it by the denominator. So let's see. First thing that goes into that, we got to factor in x squared into that, which would give me an x to the 4th minus 2x cubed minus, plus x squared. And we're going to subtract all 3 of those. And just by the luck of the draw, wow, this is really nice. Those cancel, and those cancel. And you bring down the 2x minus 1, which means you don't have to do any more long division because now the remainder is smaller than what you're dividing by. So I can now rewrite my problem. So back over here on the left, this whole fraction now becomes x squared plus your remainder divided by the original denominator, which is x squared minus 2x plus 1. Now, unlike the one we just did, this one actually does now become a partial fraction problem because the original denominator on your new fraction still factors. So I can rewrite this as x squared plus 2x minus 1, and the bottom of that fraction factors into x minus 1 all squared, which is actually a case 2 partial fraction. So on your homework, when you're just breaking this down, so here's where your final answer comes into play. The x squared is not a partial fraction, so you would just bring that down. This fraction can be broken up into 2 fractions in the decomposition. The first one would be an x minus 1, and the second one would be an x minus 1 squared. But since they are both overall linear factors that are broken down, you just need coefficients on top of constants. So that would be a and b. Now on your homework, I have set it up to where on this type of problem, I don't want you to go any further. We could. This is actually one we can actually do by hand, but I'm not going to make you do that. We can actually just stop right there. So the final breakdown of this problem is you would have to solve the x squared plus a over x minus 1 plus b over x minus 1 squared. All right, and then to show you one where long division is not involved, what about this one to wrap up this video? You've got x squared plus 5x plus 2 over x cubed times x squared plus 1 over times x squared minus 9 all squared. Now, this one looks like it's in the most factored form, but it's actually not. Yes, x cubed is factored. Yes, x squared plus 1 is an irreducible quadratic, but technically, x squared minus 9 is a difference of squares, so we would have to break this down a little bit further. This would be x squared plus 5x plus 2 all over x cubed times x squared plus 1, and then you would factor this into x plus 3, x minus 3, all of that squared. This now allows you to distribute the squared to both terms, which will give you x squared plus 5x plus 2 all over x cubed times x squared plus 1. Then it becomes x plus 3 squared times x minus 3 squared. So that is the fully factored denominator now. So now you can see this one you don't have to do long division because the power on the bottom is very obviously bigger than the power on top. But now you've got to break this down into the number of fractions, and there's going to be a bunch of them here. X cubed is actually a repeated linear factor because that would actually be the same thing as x plus 0 all cubed. So that means you will need 3 fractions just to break down the x cubed. One of them would be an x, then you would have to do the x squared term, and then you would have to do the x cubed term. X squared plus 1 is a singular irreducible quadratic, so it only needs 1 fraction. X plus 3 squared is a repeated linear factor, so you need 2 fractions for that. 1 for the x plus 3 and 1 for the x plus 3 squared. And very similar, it's the same thing on the last one. You would need 1 for the x minus 3 and 1 fraction for the x minus 3 squared. Now going from left to right here, let's write down what all of our constants or terms would be. Since majority of these are linear terms except for the fourth one, it's usually just going to be a bunch of letters here. So you're going to have an A, a B, a C, because those are all repeated linear factors. Since x squared plus 1 is an irreducible quadratic, I have to actually put a dx plus e there. And then since the rest of these are just repeated linear factors, it's a bunch more constants. It would be f, g, h, and I. And then from there, I guess hypothetically, we could then solve for all 9 of those letters, but that's not something I would ever make you do. We would just need to be able to break it down. So that's one where we would definitely let in another class or something, let a computer algebra system do that for us, because that would take forever to do by hand. So that ends the video on 7.4, which is partial fractions. So a lot more algebra-based versus trig-based. So make sure that you understand all 4 cases of partial fractions, along with when you have to do long division instead of partial fractions.